Hey everybody, I hope you had a fantastic Thanksgiving break. Welcome back to physics class. Sorry I couldn't be with you today. Today what we're going to be doing is wrapping up your friction lab and as well as looking at some examples of friction problem solving. So before you attempt the bell work, let me just remind you of how friction works. We have our basic friction equation. Coulomb's law of friction assumes the force of friction depends on two things that determine the stickiness between surfaces, the texture of the surfaces, and then the normal force, how hard they're pressed together. You're going to be measuring this texture, this coefficient of friction today. And remember that this is the Greek letter mu. That will be important for the bell work.
Okay, so here's our bell work for today. Now I'll admit I had a little too much fun making this bell work, and it's a little quirky, so it's not truly a physics question, but it's actually somewhat of a riddle or a joke. So here we go. Two cats are sitting on a slanted tin roof. Which one slides off first? And the answer, of course, is the one with the smaller mew. Mew. So, yeah, the smoother cat, the one with the lower coefficient of friction is the one that slides off first. And of course, I had to put an alligator at the bottom because if you're going to have a cat slide off the roof, you might as well have an alligator at the bottom. And as if that wasn't enough, there you go. How do you like it? Here's our actual pun of the day. A bicycle can't stand on its own because it's too tired. You know you missed it over break. You know you did. And just for fun, because we're talking about friction, I've included a couple video clips that deal with friction. The first one is someone struggling with not enough friction. This one's been on the internet for a little while, so maybe you've seen it before. I never get tired of watching that one. And then the second one is some sort of manufacturing situation. I have no idea what this guy's making. He's going to turn his lathe on. We know that friction produces heat. It excites the molecules. And the pieces get welded together, which is super cool, or hot. Again, what in the world could that be? I'm not sure, but this guy is apparently making a lot of them. Because if you look in the background, there's a whole room full of them. All right, so here's how the lesson is going to go today. The first thing you're going to do is watch a video where I work through some additional examples with friction. It'll kind of remind us of how to set up and solve these problems, as well as tackle some problems that bring together all the ideas that we've learned about in this unit. Probably good to do a little review at this point, assuming that you might have forgotten a few things over the long weekend. And then finish collecting your data. So you'll finish part 4 of the lab. And you'll have some time, a chance to ask questions if you got hung up on anything before you turn it in on Thursday, but the lab will actually be turned in next class. So you'll have the lab due, and you'll also have homework 4H. There's no reason that you shouldn't be able to get the lab done in class today and turn it in. The only reason why you'd hold on to it is if you had some questions you wanted to ask before you handed it in on Thursday. So I'll see you then. So enjoy the rest of the lecture, work through the examples on your supplemental packet or the packet that I gave you, that fat packet, and then you can get together in your lab groups and complete the lab. Good luck and have fun.
Okay, so we're back at our friction lecture problems. We've worked through some of these already, like the pushing of the refrigerator and then the sliding of the dingo's kidneys. Now we're going to take a look at a baseball player sliding into second base. You have a homework problem very similar to this, so I think you'll find this helpful on your homework. So if you haven't heard of Chase Utley before, he was in the news several years back in the baseball playoffs for causing a bit of a controversy in terms of one of his slides. So he was the inspiration for this problem. So check this out.
By a defensive back. Check this out.
This was going to be a tough turn anyway. The ball behind second base, he was going to turn that way to make a throw. Utley got off on a great secondary lead, and he gets right there to break up the double play.
Didn't even start sliding till he was even with the bag. This is a play you used to see it happen a lot 30 years ago. Very rarely see it happen now. What a collision.
This problem isn't so much about a dirty slide as it is just about my curiosity as to how much friction exists between a baseball player and the ground as the baseball player slides along the ground. So what we'll do is we'll approach this problem like we would any physics problem by drawing a picture, turning this into something we can see. And I'm going to draw the baseball player sliding head first simply because it's easier for me to draw. And so we're given some information about this baseball player. We're told how fast he's going. So we can go ahead and put that in as his starting speed, 8 meters per second. And we're told how far he slides, 3.66 meters. So we're going to go kind of old school style here. And you remember doing this, writing out a beginning and ending position like this. This is going to become important, as we'll see later. And we also know his mass, 80 kilograms, which, in case you're curious, I looked up for his stats. And so given this information, which looks kind of like a kinematics problem, we have to figure out our coefficient of kinetic friction, or what the roughness number is between a baseball player and the ground. So it may not be obvious how to go about solving this problem, but I need to start someplace. And if you look at your equation card, there's only one equation you have that has mu in it, the coefficient. So I must somehow use this equation to find mu. So in order to find mu, there are two steps that I have to make along the way. I have to figure out the normal force of the baseball player on the ground, and I also have to find the friction force. And if I can plug numbers in for those, then I can find mu, and there's no other way about it. So what I'm missing here, of course, is my free body diagram. So I'll do this next. I'll draw the forces that are acting on Utley. We got the force of gravity, which is his weight, and we have the normal force from the ground. And as he slides to the right, there's going to be some friction, specifically kinetic friction, acting to the left, slowing him down. Now, a lot of times people will want there to be a forward force acting on him as well. In this case, there is no forward force. His inertia is carrying him forward, and friction is causing an acceleration that will make him stop. We actually expect that acceleration to be a negative acceleration in the direction of the net force. So from this, I can see, or hopefully can see, that finding the normal force, my one missing piece, shouldn't be too hard. That there is a balance in the y direction. He doesn't move in the y direction. Those forces cancel out. So if we know the force of gravity, by default we also know the normal force. So first step is to solve for gravity, multiplying his mass by 9.8. 80 times 9.8 is 784 newtons. So the player weighs 784 newtons, therefore the normal force from the ground is also 784 newtons. So we're halfway there. We've got a number for the normal force, and we're solving for mu. We only have one missing piece of information. We need to know what the friction force is, and then we can find our coefficient. Now the second part's a bit trickier. For the first part, we were basically using the idea that the forces in the y direction have to add up to 0. They balance. In the x direction they won't, because there's only one force in the x direction, and that's the force of kinetic friction. So I'm going to use this information to solve the problem. I'm going to have an F equals ma scenario in the x direction, not a net force equals 0. And I'm going to specify that I'm just talking about the x direction here. So my net force in the x direction produces acceleration. So if I add up all those x forces, the only force I have in the x direction is the force of kinetic friction. The only force in the x direction is the force of kinetic friction. So that's going to be my net force. And we're going to find it using the x variables. Then we'll have a number to plug in here to find mu. So far so good. We know the player's mass, 80 kilograms. Oh no, here's where we're stuck. We don't know his acceleration. So you knew somehow we're going to have to use these variables up here. So this becomes a kinematics problem, one where I have to use my knowns, and if that's helpful to you, list your knowns out again, and we can use that to solve the problem. So let me come down here, a little bit of space here, and write my knowns out, starting and ending position, starting and ending velocity, acceleration, and time. Remember doing this? He starts at 0, he goes to 3.66 meters. His initial velocity is 8 meters per second. He's sliding into the base. He has to stop at the end, so his final velocity is 0. We don't know acceleration. We don't know time. I should be able to find a kinematics equation that will let me solve for acceleration, not needing to know time. So there's one on our card, the only one without time in it. And so we'll be using this equation without time in it to figure out his acceleration. So let's see, what does that give us? Ending velocity is 0, beginning is 8. And don't forget to square that. 2a 3.66 meters minus 0. I'm going to crowd that in there. Okay. So I can solve for a, and unsurprisingly we get a negative acceleration, which is what we're expecting. He's going to accelerate to the left, and it's going to slow him down and bring him to rest. Negative 8.74 meters per second squared. So our work here is basically done. Now I have a number I can plug in for acceleration. 8.74 meters per second squared. And I can solve for the force of friction. The force of friction slowing Chase down ends up being just under 700 newtons. And so then that leaves me with a kinetic friction force of 699 newtons. And it may seem that I've forgotten something here, but I notice I didn't put, it's a negative force, but I just put the size of the force. This is not a vector equation. It's the size of friction and the size of the normal force. You never have a negative friction coefficient. And I know there are a lot of steps to this problem, but now we're done. We can do our last division here, 699 divided by 784. And we found the roughness number between a baseball player in the dirt to be 0.89. And I'll be honest with you, when I got this answer, I got a little surprised because this is a rather large number. It's maybe close to what you'd find with a tire on pavement. And I think, you know, as I reflected on this problem, is that a baseball player is probably quite a bit smoother than that as he slides on the ground, but the baseball player doesn't slow down and come to rest right as they reach the base. They're probably going to be moving pretty fast, and most of the stopping probably occurs running into this bumpy base. And so our friction coefficient is basically telling us the roughness of a baseball player hitting second base for the most part. So there we go. Use this as an example. You have a sliding example in or a problem to do in the homework. This can be a helpful sample for you. Last problem we're going to do is this Grinch problem. It's getting to be that time of year. And we're going to solve this problem. It involves an angle and friction. So it really is going to bring together a lot of the things we've learned how to do in this problem solving. And I bet there'll be a question like this on the test because it brings so many different ideas together. So it looks complicated, but it's not too bad. I know it's a multi-part problem. We're just going to do part A here and then call it a day and move to our lab work. Okay, so let's check out this problem. The Grinch applies 612 Newton pull. The rope's at a 15-degree angle. We know the mass of the sled. We know two roughness numbers, one for static, one for kinetic. And we know that the sled is in motion horizontally at 5 meters per second. So we're going to start by drawing a picture. And here's where we get to have some artistic fun. And we'll draw the sled. And it looks something like this. And here's all the Who's possessions in the Grinch's bag here, tied shut. We got a mass, 835 kilograms. And if you want, we could draw his little dog. It's his name, Max. We'll draw Max on the sled here with his reindeer antler. And then we'll have the Grinch. You're a mean one. Oh my gosh. Let's see. He's all leg, apparently. You're a long-legged one, Mr. Grinch. There we go. His little Santa hat and his cruel smile. Okay, so there's the Grinch. He's pulling the sled. And we got some numbers that are given to us here in the problem, so we'll bring those numbers in as well. We know his pull is 612 newtons. My goodness, rings my cell phone. All right, sorry about that. So we got his pull, which is 612 newtons, and we've got this angle, which is 15 degrees that he's pulling with. We're also given our two roughness numbers, our coefficient of kinetic, 0.21, and our coefficient of static, if the sled isn't moving, is 0.35. And we're told that this sled is moving to the right at 5 meters per second. So there we go. I think I brought everything into this, and we need to find the sled's acceleration. So it's not going to stay at 5 meters per second. It's going to either speed up or possibly slow down. It's up to us to figure out by how much this will happen. So before I go to use an equation, I'm going to draw my free body diagram so I can think about all the different forces that are acting on this sled. We have this tension force created by the Grinch, which we know to be 612 newtons. We've got gravity, which is the weight of the sled. And though we're not given it, we can find the force of gravity by multiplying the mass of the sled by 9.8. So let's do that. 835 times 9.8 gives me a gravity force of 8,183 newtons. We have a normal force of the ground, and because the sled is in motion, we have some kinetic friction acting to oppose that motion. And we don't know the normal force or kinetic friction. It's of course tempting to think that the normal force is the same as gravity, but there are two upward forces. So remember that if you break the tension into its components, there's an X component of tension and there's a Y component of tension. And the Y component of tension together with the normal force are going to cancel out gravity. So makes the problem a little bit more complex. Okay. All right, so we're going to find the sled's acceleration. We've got our pictures drawn. That's all taken care of. So this is obviously an F equals ma problem. And it's a two-dimensional problem, so we're going to deal with the X and the Y direction separately. The motion of the sled, and therefore its acceleration, is in the X direction. So we're going to use the X direction to find the acceleration. So on the left side of my equation, I'm listing out all the forces that are acting on the X direction. I look at my free body diagram. There are two of them. There's friction and there's Tx. So Tx plus kinetic friction, and together those add up to produce an acceleration. Well, there's a lot we don't know here. We don't know what Tx is, but we can find it. It's the X component of the tension force. So remember, to find an X component, we take the tension force of 612 newtons, and we multiply it by the cosine of the angle. In this case, it's a 15-degree angle. It's this angle right here, 15 degrees. So that gives me its X component. Then we have our friction force, which we don't know either. We have the 835 kilograms, and so we're so close. If only we know the force of friction, we could determine our acceleration. So how am I going to find the force of friction? Well, in order to do that, let me come up here. I don't have a ton of space here, but I'm going to use my friction equation. I do have an equation that tells me the force of friction. It depends on the coefficient and the normal force. And we are given a coefficient. This is, make sure to use the kinetic one and not the static. The coefficient is 0.21, and doggone it, we're stuck again. These multi-step problems. A lot of times this happens in a physics problem with lots of steps where you're working, you're trying to solve for things, you get stuck, so you have to go to another equation, you get stuck and go to another, and we kind of work our way backward. So solve for what you can solve for, and then look for new equations if you get stuck. So in this case, we're stuck, we don't have a normal force. So in order to find the normal force, I'm going to ask myself not about the X direction, but the Y direction where the normal force is. And since the sled only moves in the X direction, I know that all of my vertical forces must cancel out. So on this sled, there are three vertical forces. There's the normal force, there's gravity, and then there's part of the Grinch's tension, Ty, and all three of those forces have to add up to 0. So in this case, I'm going to solve for the normal force. Fn, we don't know. Gravity, be careful with your sign. Gravity points downward, and is 8,183 newtons. And Ty we don't know, but we can find. It's going to be 612 newtons times the sine of 15 degrees. And all of these forces have to add up to 0. And so we can solve for the normal force. When I find Fn, I get 8,025 newtons of normal force from the ground. And then the rest should all fall into place. Once we know the normal force, that's here. We can go bring it up to this equation and figure out our force of friction. Friction force is 1685 newtons, resisting the sled's motion. And once we know the friction force, we can bring that down here to this. And again, be careful with your signs. The friction force is acting to the left. And so I'm going to put negative 1685 newtons in here. And so the friction force is actually going to be, the negative force is going to be a lot bigger than the positive force pulling it forward. The Grinch doesn't have the strength of 10 Grinches yet. Apparently his heart is too small, and so he's not pulling hard enough. The net force on the left side of this equation ends up being negative 1,094 newtons. And so therefore this sled is going to accelerate in the negative direction, meaning it's going to slow down and lose speed and never make it to the top of Mount Crumpet. at least not at this rate. And so we get specifically a rate of 1.3 meters per second squared, that it's going to slow down at that rate. Okay, so I know this is definitely the toughest question we've seen so far. There are a lot of different parts to this, and I probably should have made a little more space here on the page. But I hope you're able to follow along well, and when you try the similar homework problem, use this as a model and make sure that you're able to work through this kind of a thing too. Be good review for all of our concepts as well. So good luck. All right, folks, for part 4 of the lab, you're going to be measuring an actual friction coefficient between two surfaces. So for this part of the lab, you're going to pick one of the friction blocks, use one of the sticky foam sides on one of the tabletops or counters here in the classroom, and you're going to measure the friction force both for static when it's at rest and for kinetic when it's sliding, and use those to calculate a coefficient. So in order for things to go smoothly, or actually roughly as the case may be, we're going to place an extra weight or a passenger on top. That will increase the normal force and will make your data collection a little easier. It's also recommended that you use or create a little loop of string to connect the block to the force sensor, and then you're going to pull on it and you'll get a graph on Logger Pro of force. You don't have to open any particular file. You can just plug this into the computer, and you guys remember how these vernier sensors work. Sometimes it won't pick the sensor up, so you might have to plug it in again or restart Logger Pro and until the sensors connect, and it gives you a graph of force. Don't forget to zero your sensor before you collect data, and when you're ready to collect data, you can start to pull on this thing. Now, interestingly, the sensor doesn't actually measure the friction force. It measures the applied force of tension in the rope. But before this thing begins to move, when it's static friction, your pulling force is going to be the same as friction because the forces are equal and opposite and add up to 0. So we're essentially getting a graph of static friction as we pull on this before it moves. Okay? Once it starts to slide, you have to be careful to pull on this in such a way that you know your pull is the same as kinetic friction the other way. Okay? You should be able to find both of those things on the graph and work through the lab. When I return to the next class, you can ask me questions if you have any. So good luck and smooth sailing.